When a new product is conceived, it usually happens in a space detached from the physical world it will eventually inhabit. In this environment, a designer's focus is pure. You look at the sweep of a surface, the elegance of the silhouette, and the function of the object itself. What you don't design is the invisible void of empty air surrounding it. But every major carrier operates on a rule called dimensional weight. They calculate the actual mass of your shipment and a volumetric figure derived from its outside dimensions, and they bill you for whichever number is larger. Read that from a designer's chair. The empty space inside your box is billed as though it were solid matter. Air becomes mass on the invoice, turning invisible volume into a permanent financial liability. When shipping costs spike, the obvious corporate reflex is to march down to the packaging team and ask them to shrink the cardboard box. Packaging engineers are usually incredibly good at this. But packaging can only ever wrap the shape it is given. If the object inside doesn't fold or come apart, you are stuck paying for the unyielding dead air trapped around it. A graceful, tapered silhouette might look beautiful on a desk, but inside a standard rectangular carton, it leaves 4 distinct wedges of billable air in the corners. No amount of clever carton engineering can recover that volume. The financial penalty doesn't actually originate from the box. It reaches backward, landing entirely on the product's fundamental geometry. Think about a traditional manufacturing expense, like the cost of an injection mold. That tooling cost is a painful check to write, but you pay it exactly once, and it is amortized across the life of the product. Dimensional weight doesn't work like that. The cost of shipping air is a recurring penalty. It is charged on every single unit, every single time it moves, for as long as that product exists. And the environmental math mirrors the financial math. Pushing volume across oceans burns actual fuel, meaning empty space drives real emissions. Because this recurring toll never goes away, physical density has to be treated as a strict design output. It cannot be left as a logistics afterthought. This reality places rigid physical demands on early design. You have to ask, does the form nest perfectly inside a copy of itself? Or is it a sweeping architectural form that absolutely refuses to share space with another unit? Can the product fold flat? Does it disassemble into individual layers that tessellate perfectly without wasting a millimeter? The ultimate logistical boundary for these questions is air freight. Cargo doesn't fly as loose boxes. It travels in unit load devices, or ULDs, which aviation authorities treat as actual aircraft parts. This diagram shows a cross-section of an aircraft fuselage. A ULD is contoured to fit inside, meaning its outline is a curve. Place rigid cuboid objects inside, and you create unusable crescents of space. Notching these boundaries means less money wasted flying air. You cannot engineer a stacking feature onto an existing design as a retrofit. A product either collapses, nests, or it doesn't. That physical trait is permanently settled early on, while the digital surfaces are still moving. This introduces a critical new question into the concept room. How densely does this stack? And what is the exact cost of moving 1 million units? The defining, most expensive logistical outcomes of a product's life are locked in before the engineering phase even begins. That means the software used to conceptualize these forms must possess an inherent understanding of physical, real-world constraints from the very first line you draw. Design decisions are practically free during a sketch, but they become financially brutal once tooling is complete. See every logistical and geometric angle before you build. Start at the concept phase with Depix.